Okay, so this is the second part. How you want to how you can analyze the system in the digital forms. So today, so in this video, I think I just cover for the stability parts. Okay, so there will be three parts. I think the first part is about the how we convert from analog to digitals, and then the second part is about how you analyze the systems in term of the stability. Okay, and then the third part is about the output characteristics. Okay, now stability. So how we can differentiate between system analysis in continuous forms and the system analysis in the digital forms. Okay, in terms of stability. Okay, so maybe I can use the explain. I think you already know how to determine either the system is stable or not for the linear systems. So here is the reals and imaginary. Okay, for the systems that the poles location at the left hand side of the S-planes, so poles at the left, Allahu Akbar, left hand side of the S-plane, so the systems is tables. Okay, so here is the systems analysis in continuous forms, whilst the system analysis in the digital forms. So we can use a unity circles. Okay, unity circles that represent how we determine the stability of the digital forms. In the digital form, so here is the reals value, imaginary value. So here is 1, 1, 1, negative 1. Right? Gapo gax. Macam tu. So it's 1, negative 1. So we call it a unity feedback. Unity circles. So for system analysis in digital forms, if we want to determine either the system is stable or not, if poles location is within the unity circles, okay, poles locations is within the unity circles, so it means that the system is stable. The system is stable. Okay, one more time. For system analysis in continuous forms, if the location of pole is at the left hand side of the systems, left hand side of the S-plane, okay, here, so it shows that the system is stable. While for system analysis in digital forms, if the pole's location is within the unity circles, so the system is stable. So let's say, for examples, you have poles with the value of z equal to negative 2 and z equal to negative 0.5. Okay, So we draw the S-planes. S-planes is reals, it's imaginary, and then here is the unity circle. 1, 1, negative 1, negative 1. Okay. So if you plot the location of poles, okay, negative 2, somewhere here, negative 2, and then negative 0.5, it is somewhere here, negative 0.5. So now the question is either the systems is stable or unstable. Now the system is stable or unstable. So now, what is the definition of stable system for in the digital form? So say that if the system is stable, the system is stable system if all poles is within the unity circles. Now the value of pole is z equal to negative 2 and z equal to negative 0.5. And then when you plot on the S-plane, only one pole is within the unity circles. Okay, just one pole is within the unity circles. So, back to the question, either the system is stable or not. So, the system is unstable system because only one pole located within the unity circles. Okay, so that's all about the stability. Now we move to how we represent the transfer functions between the Z transform and the state space. Okay, what is the relationships between both? Okay, so as you learned before, okay, I just do some recap. The task is already go through everything here about the state space, equations, standard forms, and then how we convert from state space to the transfer functions. There are some equations that you have to use and so on. Okay, now, so in the state space form or in the continuous x dot t equal to axt plus but and yt equal to cxt plus dut. Okay, so now as you can see here, everything is the form of time domain, so the system is continuous systems. And how we convert from state space to transfer functions by using the equations ys over rs equal to c st minus a negative 1b plus d. Okay, I think Dr. Rizal recovered the early chapter in these courses. Whilst in digital control systems or digital forms, here is a continuous here in the digital forms or digital control systems. Okay, same state space equations. X equal to Ax plus Bu, okay, bracket, and then y equal to Cx plus du. So same goes to how we convert to state space to transfer functions. Okay, y over r equal to c I minus e minus 1b plus d. Okay, so obviously in the continuous system or continuous forms, we use t, okay, in the time domain. Okay, so everything in form of t is represent time domain. So now in the digital control systems and digital forms, t will be replaced to k. Okay, in continuous forms or in time domains, everything in the time domain form or t. Then we convert to digital control system or digital forms, t will be replaced by k. And one more thing, okay, t will be replaced with k and s will be replaced with z. So now we replace it one by one. Okay, k blue value, k blue color. Oh, okay, one mistake here. It's not x dot, it's just x. So here is x. Different with the continuous forms is a x dot t, while in the digital control system here is x only. Okay, now we go through one by one. So we hold for the x, the first variables. Okay, we go to the second first, ax. So axt become axk. But becomes buk. Yt become yk. Cxt become cxk. Dut will become duk. Okay, now. So you know that, warna apa? Purples. Okay. You know that x dot t is a future value. So how you want to convert x bracket to the future value without the x dot? So x dot t is a future value. So in order to make this variable as a future value as well, okay, so current value is xk. So future value will be x k plus 1, right? So here's the current value, here is the future value. So now in order to make it similar, x dot t is equal to x k plus 1. Okay, so this both is the future, represent the future value. So here is k plus 1. Okay, so I repeat again. In the continuous forms, the first variables is x dot t. Okay, so everybody know x dot t is a future value. However, when we convert to the digital forms, the first variables we use x in the bracket. X in the bracket. However, x in the bracket must represent the future value as well. The future value as well. And we also know that if xk is a current value, okay, current value. So to represent the future value, so we use x key plus 1. So that's why we replace or we use here x key plus 1 to represent the future value similar with x dot t. Oh, while in the frequency domain and Z transforms, so we have S here, S, and S. So we replace S with Z. So it's become YZ, RZ, okay. And another one is ZC, ZI minus E, negative 1B plus D. Okay. Okay, so one examples. Cukup tak? Okay, one examples. So the questions I haven't write down. Okay. Ta-da! So it is questions. Okay. So we have how we want to convert from the transfer functions to the state space. Okay. So the transfer function in Z form, while the state space in the K. How you want to do it? So the higher order for the denominator is power of 3. So here is the third order systems. Okay. The third order systems from transfer functions to state space equation. So third order have x1 key plus 1, x2 key plus 1, and x3 key plus 1 equal to, here is x1 key, x2 key, and x3 key plus the bracket E. Dalam sikit. Plus U K. Okay, write it back from transfer function in Z form to the state space in the K. Okay, while for K, Y key equal to Y1 key, Y1, X1 key, X2 key, and X3 key. And if you still remember, the denominator represent or for matrix A, while the numerator is for matrix C. Same goes to the digital forms. Okay, so you have to write it from right to left from here. Okay, so this is a matrix. So here is negative A3, negative A2, negative A1, and then The other matrix is the same, 0, 1, 0, 0, 0, 1. While for the B is 1, 0, 0. 0, 0, 0, 0, 1. Okay. And same goes to the numerator. We write from right to left. So here it become B3, B2 and B1. I think Dr. Aziza already go through this. Okay. Okay, so this is how we convert from state space to transfer functions and vice versa. So in this case, first we convert from transfer function to state space, and then it goes same methods when we convert to state space to transfer functions. Okay. Examples. Normally in the test or the final exams, the pattern of the question. Okay. Let's say you have one systems. One system. Here is the input RS. Okay, so here in the frequency domain lah. And then there the sampling T. Macam tambah pula T. And then dia ada satu, it has a zero order holes, y minus exponent minus st over s. So satu is one system in frequency domain 3k over s plus 1, and then the output cs. And then we have a feedback. Yeah, is plus and negative. So okay, here's the questions. So what is the first step in order to analyze the system? Obviously, you have to convert it first to a digital forms because it have a zero order holes here. Zero order holes. So the function is to convert from digitals to analog to digitals. So here the analysis we do it in the digital form. So normally the question will be some things. First you have to convert the system to the digital forms. Second, you have to determine what is the range for k in order to make sure the system the system stables. And the last one, what is the output characteristic? So this normally the 3 questions will be asked in the either your test or final exams, etc. So in order to solve these 3 questions, the knowledge that you have to know is first, okay, I will show the examples. First we go through what's the it's the information or the knowledge you have to know or to have in order to solve the 3 questions. Okay, number 1, you have to know that z is equal to exponent st. So this the conversions or the relationship between z and s. And then number 2, you have to know how to use partial fractions. Partial fraction. Okay, so it's a mathematics relationship equations. And the third one, you have to know how to use Z transform tables. So these 3 things you have to know. You have to know how to use the partial transform Z transform tables. You have to know how to use the partial fractions methods or equations is math. And you also have to know that the relationship between Z and S is Z is equal to exponent ST. So we go to the next video for how we want to solve these 3 questions. Okay guys?